Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have Rob Miller from MIT telling us about crowd computing.
All right, thanks very much, Adam. I'm going to talk to you about the work that my group has been doing at MIT for the last couple of years. In the area of crowd computing, which we choose as a name and as an intentional analog to cloud computing, as we, in the same sense that cloud computing is about having access to highly available and elastic computational storage resources over a network, crowd computing is the same thing but with human resources. And in particular, we want to look at how to use those human resources to solve problems that a single person would struggle with and that we don't know how to do with software yet. So this is sort of an example of an incredibly hard handwriting recognition problem what's that? Did I write this? No, one of my grad students wrote it. But used his non-dominant hand and tried to be shaky. But we do see realistic examples of this. This is sort of a toy example. We'll see later more sort of practical ones. But the notion of crowd computing is getting a large group of people on the web, and these people are now available in a variety of different systems. Some of them are mentioned here. To make small contributions each. So we're not depending on a huge amount of work from any one person to do things that we don't know how to do with software alone. AI is not up to the task yet, and that one user alone would struggle with. And there are lots of motivations that power these crowds. Wikipedia has made huge hay out of purely volunteer work. Some of it small contributions, some of it large. Fun is a great motivator. This is a screenshot over here on the right of Fold It, a game at University of Washington, made by University of Washington that has random people on the web folding proteins. And they've actually published a number of papers in Nature and Science that came out of the players of this game and have much longer author lists than most science papers. Social is another way that you can draw a crowd. So one way that I think about Facebook is a large global face recognition problem that people are solving because they're tagging their friends in the pictures that they're posting on Facebook. And then there's pay. And Amazon Mechanical Turk turns out to be a really nice platform for prototyping many of these ideas. How many people have seen or used or heard of Mechanical Turk before? Good. The best features about it is that it's programmable. You can write code that will post jobs in Mechanical Turk, collect the results, and pay people, and do all of that automatically. So you can actually think of using this kind of crowd behind a system that you're building. We also think about using it as again, a prototyping platform, a place to try out ideas for crowd systems that maybe someday would instead be implemented on a different kind of crowd, not one driven by pay, but maybe one driven by volunteering or social or fun. So that's the big idea. For the rest of the talk, I'm going to show you, first of all, sort of some of the low levels of this, the way that we think about programming a crowd. And then I'll show some examples of crowd-powered systems that we've built, so systems that have human intelligence behind them in the form of one of these highly available crowds. And I want to finish by pulling back sort of another step and thinking about what the design space is now when we have crowds as one of the components that we can use in a system design and where we're going from there. So for the first part, what I first want to illustrate is a feature that it seems like almost every crowd has. This is a task I like to put on Mechanical Turk. Mechanical Turk is particularly demonstrative of this feature. This task just asks a person to flip a coin and tell me whether it's head or tail, and I'll pay them a cent to do it. And I do this task over and over. This particular one I only ran 100 hits, but we've also done it with 1,000 hits, and this is pretty much what you get. Which either shows that there's a lot of unfair coins out there, or there's not a whole lot of coin flipping going on in this group. This also doesn't add up to 100 because the 100th person had a binary coin or something and gave it something we didn't even ask for. So there are many interesting questions you could ask about this, right? If you change the instructions, it does actually change the results. If you put T for tails before H for heads, the effect kind of goes away and it goes back to 50-50. That's actually, I'm not interested in any of that. I'm an engineer. From my point of view, this is noise, right? And so we need to design our system so that it tolerates this kind of noise that we're getting from the crowd. In Turk, some of this noise comes from genuine spammers, people who are answering randomly just hoping to get paid. In any crowd, it's going to come from people who don't understand the task or who are not giving it their full attention. Or human beings make mistakes. So that sort of is the key problem that we're going to try to solve with more careful system design. I want to come back to this example that I presented at the beginning, this very hard handwriting transcription problem. One person alone, turns out, has struggles with this, can't do a great transcription. So we developed an algorithm that uses iterative improvement by many workers in order to get a decent answer. And I'll just briefly illustrate how that works by showing sort of the middle of the algorithm. So we have a partial transcription right here that a new worker is being hired to improve, basically being paid 5 cents to just fill in one additional word here or correct a word that was mistaken. And in this UI, this is a somewhat older version of the UI, but workers can indicate when they're uncertain about things by putting parentheses around them and leave question marks for places that they don't know. So that person's asked to make an improvement, and so they make that improvement, and then what we do is take their input and their output, feed it to a group of voters, each of whom are paid a small amount to just say whether this input is a better transcription or whether this output is a better transcription. And these are presented in a random order so the voters don't know which was the input and which was the output. And then the winner of that vote, either the input or the output, goes on to another phase of this algorithm. And hopefully we're climbing a hill here. One of the challenges here is figuring out when to stop the thing. We could have another phase where voters are deciding whether it's complete or not. At the moment, we just sort of cut it off when the requester, when it looked to us like it was complete. And at least in this particular example, the crowd actually does a pretty good job. So they still have some uncertainty in some of these words. These red ones here are places where the crowd got it wrong. This should have been flowery. That should have been get instead of got. Should have been verbiage, and that should have been the person's grade, B-. But one thing I'd point out here is that groups of people are good at solving problems. And that even when they get it wrong, the way that they get it wrong is actually somewhat sensible and fairly close to what the original was. Here's another example. So this is a blob of printed text that we've applied a Gaussian blur to. I have trouble making anything out of this. But apparently there are enough people on Mechanical Turk who can, because after 8 iterations of that process, they pretty much got it all right. This word here should be wedged. Where does that come from? Here? I don't know. Human beings working in groups are somewhat magical if you can coordinate them the right way. So that's our first example of a simple but fairly effective crowd algorithm that at least we call improve and vote. Algorithm, workflow, design pattern, there are many words for this. When human beings are involved, it feels a little iffy calling it an algorithm.
The last example, could some machine learning thing have done it, or you guys?
Probably, yeah. We didn't, yes, I would not be surprised, given that it was a very mechanical transformation that we did. What we were mainly doing here, these are toy examples that are mainly designed to test the idea of the improve and vote algorithm, and not intended as things that we don't think could be automated.
The members of the crowd restricted in what means they can use?
No, they were not.
Machine learning programs themselves?
So they may have tried to plug this into Photoshop, for example, and unblur it. That's a possibility. I think that's fairly unlikely for the sophistication of the crowd that we have, but certainly for tasks like translation from one language to another, you do see the crowd trying to reach out for automated tools that are available to them and take the easy way out. And in general, we don't want them to do that, and we have to sort of design in things that will prevent them from doing that.
So you just said that for the sophistication of the crowd that you had, do you have measures of what capacities, what resources they have at hand? So it would make a lot of sense that if somebody saw this, they'd recognize right away what kind of blurring tool was involved. Somebody's at all familiar with Photoshop, they'd know to grab that and de-blur it. So,
It's possible.
okay.
It's possible.
But your sense was that wasn't likely?
My sense is that that was not happening. Yeah.
And what's that based on?
That is, yeah, that may just be a gut thing. You're right.
It's not clear you can de-blur and de-blurring doesn't, it's not, you can't in general just de-blur and cover all the information. It's not necessarily an operation that works. I mean, if you have a blurry photo, sometimes you can, but not
Oh, no,
always.
no, but, yeah.
If I understand correctly, none of these questions are particularly relevant to what Rob has to tell us.
I think mine was.
They are still interesting questions that I'm willing to, I'm willing to
It's
discuss.
just debugging the algorithm. It's got nothing.
No, you're right, and you've actually pointed out something that I do, which is that I sort of assume that Mechanical Turk workers are going to put less effort into it than what you just described, because we are paying them 5 cents for this. On the other hand, somebody who is really an awesome Photoshop hacker might be willing, just for the fun of it, to crank up Photoshop and solve that problem, even though it's 5 cents.
8 changes were sort of gradual, or if there was a jump? Do you
Oh,
know
if
that
there was a
then-
sudden transition, great question. I would have to look at the data, because that would answer that question. If there was one person in there who was like a ringer
Yeah.
that had some tool they knew how to use.
Yeah.
Good. I would have to go back and look at the data. Okay. Few things I wanted to say about this. Main thing is sort of what are the criteria that we want to think about for comparing different workflows, different algorithms. One is how well it deals with noise. And one of the reasons I like Mechanical Turk as a prototyping platform is because it is very noisy. Our rule of thumb is that for any given piece of work, any given hit, you put out in Mechanical Turk, 30% of the time you're going to get some bad work back as a result. It's not always going to be like spam. It's not just going to be like garbage they've typed in there, but it may be somebody who does not paying attention to the task or didn't understand the instructions. So we have a fairly high noise rate, which really forces us to think about quality when we're designing the system and think about quality control. My rule of thumb is if it works on Mechanical Turk, it's likely to work on any given crowd, because Turk is kind of so bad for that. This particular algorithm runs very slowly because it's serialized, has to pass through all of these stages, and you're not really taking advantage of the fact that you have a big group of people who could be working in parallel. And we have to think about the incentive. So in Turk, this is simple to measure because it's the number of, it's the amount of money that you had to pay these people in order to get them to do the work for you. It's harder to quantify that when you're talking about, say, a social crowd. How much social capital did I expend by making my friends do this bit of work for me? We'll see a couple of other algorithms later when I talk about these other systems. I just wanted to start with that one because it's simple and shows some interesting results. So next, a couple of systems that we've built that are a little bit more practical and show the value of having human beings inside a system. So this is a problem that we unfortunately still have a lot. I don't know why we still have page limits in the age of digital publishing, but we nevertheless do. And so 30 minutes before a deadline, you know, this is page 10, we find ourselves with a little bit over, and we've already played all the tricks we think we can play with font sizes and line spacing and margins and things like that, and we're still a little bit over. And the author, you know, the user, the single user that is working on this paper, they really should be paying attention to things other than the length of the paper. They should be focusing on getting the content right, because it's going to be accepted for its content, not for its length, right? It could be rejected for its length. It won't be accepted for being on 10 pages. So the idea is to let that user focus on what's important and hire a crowd or obtain a crowd somehow to focus on that other problem. How do we deal with its length? And I'm afraid my video did not seem to be working when I was trying this at the beginning, but I'll sort of talk through how the thing actually, oh, video is working, good. What we do is we take the user's text, and we just sent off a bit of the conclusion to the crowd. And some minutes later, we come back with suggestions from the crowd for how to shorten this thing. And it's now embedded in a user interface with a slider here that automatically chooses from those suggestions in order to fit to exactly the length that you want. So you can kind of drag your paper down to 10 pages, and you've got exactly what you want. And that UI also showed you what was actually changed, right? So that you can compare the before and the after and basically monitor the crowd. So this is something that we'll come back to later, sort of this synthesis or this symbiosis between an end user and a crowd of human editors, human intelligence, and software, in this case doing something fairly simple, that is a greedy search among all of the suggestions in order to fit the length that the end user is trying to shoot for, that brings it all together, that coordinates it all.
So what decided what fraction of the comments you were going to take and what fraction you're going to discard? When, say, you want to shrink it up to a certain point, so did you have are you going to describe how you, or what, who determines which comments to include and which comments to reject?
Yes, so the comments actually have already been put through a filter, and I'll talk about that when I talk about the workflow algorithm. So all the slider was really doing is saying, I have a certain desired character length. Give me a subset of the replacements that will get to as close as that character length as it can.
Mostly just the length that matters. It's not the quality.
At that point, it's the length, and yes, we haven't graded the quality anymore finally, other than throwing out the worst, and that's what the algorithm I'm about to show you does. So the way that this works, the workflow that the crowd went through when it got that pile of text to work on, is this find, fix, verify pattern that actually splits up the editing into two different phases that allows us to do some more quality control and treat those edits sort of independently and be able to choose between them independently. So the first step is just to find a place that looks like it needs editing. In this case, it's a place that is kind of fatty, right? This sentence could be reworded to be shorter. Those workers simply have to highlight that. They just have to mark that as a place that could be shorter. Then the advantage of that is that then we can get sort of independent judgments about places that are fatty, look for at least two people saying that that is a fatty bit of text, and pass only those on to the next step, which is to rewrite them and make them shorter. Right? So this gives us some quality control for that. If we were just, and we did do some experiments in which these were combined and said that here's a paragraph, shorten it, you ended up with a lot of changes to the paragraph that were much harder to do quality control on. So this allows us to get what you saw in the demo, lots of little changes to the text, which is actually very interesting because it means the crowd is behaving differently than a single editor would behave. And then the fix is make a change that will shorten it without changing the meaning of the paragraph. And then because some of those will be bad, at least on Turk, our rule of thumb is that 30%, a third of these answers are going to be bad. We pass that on to a set of voters who basically throw out that lower 30%. And that way, what we've got back are hopefully fairly high quality choices that we choose among. So we've run this on a number of different kinds of text, including technical computer science papers, some that were already published. And people were able to shorten them. Actually, an interesting thing that the Mechanical Turk crowd does, and most of them on Mechanical Turk apparently don't have much computer science technical knowledge, is they stay away from those parts. Right? They don't delete things they don't understand. They go for the wordy English and shorten that. And that's good. At least for the parameters we chose, we tend to get about 15% cut from the text on average, which means it would take an 11-page paper and cut it to about a 10-page paper. And it does it, again, in an interesting way. It's kind of like shooting a shotgun at that paper rather than taking out an entire section, which is what a single author under a time pressure would do. It costs about as much as a professional proofreader to do it, but instead of taking an hour or more for that professional proofreader to turn it around, we can turn it around in 20 minutes. In fact, a lot of this time, so we actually split the time that it takes into wait time, which is time with the Mechanical Turk hit, waiting for somebody to pick it up. A lot of time is spent with nobody working on the task, right? So this is basically wasted time that the process is stalled, waiting for some resource to discover it and work on it. The actual work time, the critical path of the process, is only about 2 minutes to get through the find, fix, and verify for a given paragraph, for an average paragraph. So this could really run very fast. You know, this is actually close to something that feels like it would be interactive speed. You push a button in your, we actually did implement this as a Word plugin, push a button in Word, and ideally 2 minutes later, you know, you've gone for coffee, you're back, and your paper is shorter. Another feature of it, by the way, we don't just shorten things, but we also do proofreading, finding spelling and grammar errors and things like that, and it actually is, it's compatible, it's complementary with the spelling and grammar checker built into Word, finds things that that does not. And in fact, we fed the paper itself through that thing and found a grammar error that nobody else had found. Even though the paper had a lot of authors, they didn't actually find this bug. So the bug is this word here. And actually, this makes perfect grammatical sense to Word because you just have to put it in parallel with produce. So shorten should produce many alternative rewrites or introduce grammatical errors, right? Word is perfectly happy with that sentence. I'm not happy with it because I don't really want our system to be introducing grammatical errors. This really should be in parallel with changing, right? Without changing the meaning or introducing grammatical errors, right? So Word will not discover that because it's semantically, you know, the difference between those is a semantic difference. Crowdproof, that is the crowd, found this. And I think it's interesting that, you know, we had a small crowd of authors. They didn't find it. But when we sent it to the crowd in Mechanical Turk, they did. And one reason for that is that this paragraph was down at the bottom of page 5. And the authors, you know, were reading the paper from the start, right? They were reading from page 1. They had to read it all the way through. So they were pretty tired by this point. And they were also paying attention to a lot of things other than just grammar. Although this is a fairly important semantic thing, everybody missed it. The crowd was given only this paragraph. And the people who did the find were told, you got to find something wrong in this paragraph, right? You have to find something to complain about in here. So they found this and complained about it.
Any other mistakes? I mean, did they find a lot of things which weren't mistakes?
Good question. False positives. I don't think they found those in our paper. There's certainly in some of other tests there were false positives.
100 things, and this was one of them. It was really this was the mistake.
Yeah, this was the only mistake that came out of this paragraph. Good point. Probably not. So one of the issues with this system is that we did have to pull the text out and present it to them in a text box. So yes, that's another way that the presentation to the crowd was distinct, you know, different from the presentation to the authors. Good point.
You say that you only paid for someone finding an error?
Yeah, we told them they had to highlight something wrong. And virtually every paragraph has something that you could quibble with. And yes, we wanted one thing.
Nobody complained about your spelling of shorten?
Well, it does happen 3 times.
Yeah.
And it's capitalized. I don't know. Everybody knows about Flickr? I'm not sure. It's a good point.
I mean, I imagine there's other paragraphs where it happens once in the beginning of a sentence, though, maybe.
Yeah, and they may have complained about that. That's right. Certainly an effect that we did get with spelling was the spell checker in people's browser would underline things, and they would highlight that.
Yeah.
So, you know, it's, again, a sign that, that workers often try to do the easy thing. Okay, so that was a word processing plugin that draws the crowd into your word processor and helps you with editing. This is a system that Jeff Bigham, who's been at University of Rochester and is going to Carnegie Mellon in the fall, developed while he was a visitor in my lab a few years ago. And what it is a smartphone app, iPhone and Android app that allows a blind person to take a picture of the world and speak a question about it. And that spoken question and picture are posted on Mechanical Turk, where workers type in a reply to that question, and then that is sent back to the blind person's phone and read aloud to them. Right? So it's a way to use this human resource, this crowd resource, to provide an ability that the end user doesn't have. Right? It's been deployed, so it's actually been out there for a couple of years now, and it is backed now not only by Mechanical Turk. Mechanical Turk is the fallback crowd for VizWiz now when no one else is available, but it also has volunteers that are answering VizWiz questions. So you can get crowds from other sources other than paying for them. And it's getting lots of questions a day from blind people. These are a few of the questions that it got during the early days. Do you see picnic tables across the parking lot? This is the time that it took for the answer to come back. One of the things that the VizWiz system was really trying to push was to reduce this wait time. The wait time of 18 minutes that we had in the Soylent experiments, where those tasks were just sitting on Mechanical Turk waiting to get picked up. And VizWiz has gotten it down to 13 seconds, which is actually pretty fast, right? That is about the time for somebody to kind of answer the phone if you're calling them and give you the answer aloud. So that's very fast. And there's two things that VizWiz does in order to reduce that time. One of them is kind of a Mechanical Turk specific thing. If you've ever used Mechanical Turk, you know that it's got a very bad user interface for workers. It's just thousands of posted hits in a long scrolling or long paged display, and many of the workers sort of just look at either the jobs that have the most available work or the jobs that are the newest. Once your task falls off the first page of the newest results, it's basically invisible to workers, and its response rate is going to shoot way down. So what VizWiz does, and a lot of requesters are doing now, is it repeatedly posts new tasks in order to keep itself at the top of, or at least on the first page of that display. The second thing that VizWiz does is it hires people before they're actually needed. So as soon as the blind person gets up their phone and switches into the app, it'll start posting tasks on Turk in order to hire somebody and have them ready to answer this question as soon as possible. And if the worker arrives before the question has been asked, then what VizWiz does is it asks them old questions in order to keep them busy and also partly to train them up and get them ready to answer the real-time question that is eventually going to arrive.
So who's paying the workers here?
NSF right now, I think. There are many business models you might imagine using for this, but
It's not like the blind people.
no, the blind people are not subscribing to this service yet.
It's almost fast enough to drive. Did anyone try to use it to drive?
What seconds for reaction?
He's working on a video one, but I don't know whether he's ready for that yet. This is in seconds. The other thing I wanted to point out here is some of these are very long. So this is an example of a very slow answer. This happened in 3 minutes for the first person. And it's also actually a very hard question because this is the wrong side of the can. Turns out blind people don't take great photographs. This is one thing that we learned from this project. Many of them are dark or blurry. The human workers are good at detecting that and making suggestions like, the image is difficult to see, or could you please turn on the lights? But this is an example, I think, of how great human beings are just at the high end, right? That human vision systems and human problem solving can look at this can and sort of see the edge of the label here and the edge of this logo and figure out that it's Goya beans and that it's chickpeas. So people are great at doing that, but it takes them longer. moving from there, so that was an example of a system that responds in sort of tens of seconds. The next system I want to show you tries to push this sort of as far as we can imagine pushing it, and get human help within seconds, within a time that might be feasible for interactive use in a user interface. This is a crowd-powered camera shutter. The idea is to get, with human help, the camera to take the picture at exactly the right time. When is just the right moment when you should have taken this action shot, for example. So the way we do it is to leave the shutter open. We take a 10-second video. That video is sent to a crowd of workers that we've got. And roughly in the time that it would have taken you to review that 10-second video on your phone, the crowd has picked a frame from it as sort of the best one, the moment when you should have snapped that picture. And there are two ways that we do that. One of them is sort of an outgrowth of the VizWiz techniques that I was talking about, which is in order to save the time of your post hanging out, not being answered on Mechanical Turk, we hire the crowd in advance. And in fact, to simplify things, we don't just show them tasks, but we give them some money just to hang around. So we give them a retainer, but instead of being a retainer like you'd pay a lawyer for months or years, it is for minutes. And this actually shows for various different retainer lengths, that is the times that workers had to wait before the actual task was ready, what the probability was that they would actually come back. So pretty much at the 5-minute retainer mark here, we get half of them back within 2 seconds, half of them ready to work within 2 seconds. The way that works is they're allowed to go off and do other things, but we really want them to stay there in front of the computer when the pop-up appears to be ready to dismiss it and actually do the work. So if you hire people for a 5-minute retainer and hire about twice as many, or at least initially hire about twice as many as you need, then you're probably going to have the right pool ready in 2 seconds. And we don't have to pay them very much because we're not actually asking them to do very much, just to stay in their seat for 5 minutes. And they can do other Mechanical Turk tasks in the meantime. But just having them there, turns out, is not enough, because if we did like an ordinary improve and vote kind of pattern with this, we would be waiting for the slowest person in this group to make their choice. And that would not be great for latency. And we'll see in a moment when I show you some comparisons that it produces relatively poor latency. So what we do instead is we guide the group through a process of iterative refinement, looking for a good place in the video and eventually narrowing it down to a single frame. So the way that works is we imagine this is the slider of the video, and we have a small group of people that have been hired. Each one gets dropped in the video at a random place. It's not playing. They have to scrub around in the video in order to find a good frame. And we watch where their scrubbers are, where their sliders are. And when some fraction, some threshold of the group is dwelling for a threshold time around the same region of the video, we make a guess that there's something interesting right there. And we shrink the area of interest from the entire video down to a neighborhood of where those people are looking, and bring everybody else into that region as well. And then we recurse and repeat. And for 10-second video, 3 phases of this are enough to get you down to a single frame. With the particular parameters that we chose, which were we're looking for at least a third of the group to be within a neighborhood of, I think, a quarter of the size of the current window, something like that. Question?
Would that still work where the most interesting frame is at the very beginning or end? Did you guys try that? Or?
It should still work because we're positioning people randomly initially. Are you worried about sort of boundary conditions of the neighborhood?
With people people scrubbing, do you lose the beginning and end too quickly?
Because they've just crossed over each other, and I mean we're looking for also a dwell time. We're not just looking for them to strike each other. We're looking for them to be within a neighborhood of each other for a minimum of 2 seconds, I think was the actual threshold that we used. So we are looking for some dwell. But there is actually an interesting point here that the beginning of a video is sort of a salient point, right? And it may be that some fraction of our workers don't like to just start from where they are and instead jump back to the beginning of the video and do a scan through it. And that's a good question. I don't know whether we saw a lot of that behavior.
I was thinking that habits might be the opposite, but I was thinking maybe people when they're scrubbing, they only scrub like sort of roughly to the beginning, but nobody actually goes.
Nobody actually goes all the way to the beginning? Right. Interesting question. One way we might solve that is to change the timeline so that it's not the timeline anymore.
Yeah.
And then there wouldn't be any salient points, and then there wouldn't be any beginning points. Here's a comparison of the algorithm I just described to you, the rapid refinement algorithm, with just getting the first answer. And at least on Mechanical Turk, this is sort of 30% likely to be bad. Somebody who's not really paying attention and not, or actually spamming us, versus sort of traditional way to do quality control. That is, you collect frames from the whole group, and then you have another group that you've also hired vote among them, right, about which ones are the best. And what you're seeing here is the over a number of trials what the frequency is of various latencies. So the mean latency for rapid refinement is about 12 seconds. That mean goes up to 16 seconds when you're just getting the first answer back, when you're not sort of forcing people to work fast and they're sort of picking at their own speed, but you also get a very high variance in that first answer. Sometimes it's really, really long. And then when you go through a whole process where you have to wait for the slowest person to make your choice, the mean is even larger and the variance is larger as well.
The retainer model, you've already retained the...
We've already retained these people, so all of them are basically starting at roughly the same time, right? We've got that crowd ready to work within 2 seconds, so they're all there ready. And it's about 5 people. Here's some examples of actual photos, actual frames selected using the rapid refinement method, and using, this is actually the algorithm that YouTube uses for a video to choose what the thumbnail is going to be by default. And we also had an expert photographer look at these videos and try to pick out a frame. So this is an example. Up at the top, we see places where rapid refinement did really well. This is sort of a typical range, and so you can compare it against what the computer vision algorithm is doing. Down here, we have an example of a failure by the rapid refinement, which in this case was caused by having sort of 2 salient and interesting points that happened to be closer to each other than our threshold, or just outside the size of our threshold, so that when the workers sort of were exploring the boundary of those interesting points, they ended up narrowing us down to the valley between them, right? And so then the best we could do in that valley was this blurry photo right here. So that maybe could be tweaked by choosing the parameters a little more carefully based on what's going on in the video. But it might also be sort of an inevitable compromise between quality and latency that this algorithm is basically making. Okay, the last system that I want to demonstrate is a bit different from the other ones that I've shown, but one of the reasons that I have it in here is because those other three systems are all using Mechanical Turk, and I hate it when people walk out of a talk like this and think all of that work was about Mechanical Turk, because it's really about crowds, and this is a different kind of crowd. There's going to be no Turk workers behind or inside this system. And what this system is a code reviewing system that we're using now in MIT programming classes, where we have the problem that we assign students thousands and thousands of lines of code to write, and we don't have the staff resources to actually read most of that code, and certainly not in a timely fashion. So they hand in a programming assignment, and they may not get feedback from their grader before the next programming assignment is due, and then they haven't had a chance to improve. So key thing we're trying to provide here is faster feedback for students. And auto grading is really not at the point where we can, give good comments about, why this code is bad. This is actually a perfectly correct factorial function, but nobody would actually want to maintain it. So the system works by drawing on a crowd of reviewers, not just a single grader that is looking at this person's assignment, but instead this person's assignment is chopped up into bits, and similar to how we chop up your paper into paragraphs, and sent to a mixed crowd, which consists of not only staff, but also other students in the class and other alumni who have taken the class before. Maybe they're upperclassmen now at MIT, maybe they're actually graduated and gone out to industry jobs. So this is what a reviewer's sort of assignment looks like. We've got these little chunks of code that we have to review. And the reviewing process happens also on the web in an interface sort of very similar to commenting that you would do in Microsoft Word or in Google Docs or in GitHub for that matter, where you can also comment on and review code. A few things are different. One is that by default, the reviewer only has to look at a small chunk of code. And we've experimented with a number of sizes for how large this chunk should be. And the right chunk, not surprisingly, is basically whatever a module is in that program. So in some of the assignments that we submit, students are basically writing standalone procedures, in which case that procedure is sort of a chunk that is reviewable. In some cases, they're writing classes, and then the reviewer really has to sort of look at the entire class. So they're focusing their attention just on that module. They have a way to go beyond that and look at all of the program if they need to. Most of our reviewers don't need to do that. They find they don't need to click on that review all code. Second, we have an automatic checker going in here and making comments. So this is basically a lint. I think we're using a check style for Java in this case. And then the reviewers have a threaded discussion. And they can reply to each other and upvote and downvote. All of them are marked by names. And this is sort of an important thing for the system as a social system. The reviewers are all identified, but the person who wrote the code is anonymous, so that they retain some privacy. We've used this in a couple of semesters now in the software engineering class at MIT. Some of the semesters, we work harder than others to recruit alums and get them to participate. This does require effort. Students we can motivate to participate because it's part of their participation grade. Alums need other kinds of incentives. These alums we recruited mainly out of altruistic impulses. A lot of them were former staff members of the course who sort of remembered how great it was to tell people what they'd done wrong. But what we're doing now, actually, we're in the process of building this system out into a more substantial social networking system, actually, in which the alums would have an incentive to come in here in order to develop contacts with current students and potentially recruit them when they graduate. We've generated a lot of comments in the system. Students are getting about an average 10 comments per submission, which is actually better than they were getting from graders. So that's an improvement. But a key thing here is that the comments are coming back very quickly. So students hand in their assignments at the end of the week. Code reviewing happens basically over the weekend, and they get their feedback by Monday. which is a very fast turnaround, and single graders were never able to do that before. And one of the things it enables us to do is give the students an opportunity to revise and resubmit that problem set so that they can actually improve their grade. Yeah.
Maybe, I mean, do the students like the comments? Can you say anything about it?
Yes, we'll come to that, actually. We have some comments at the end. But yes, for the most part, students actually demand this kind of feedback. Occasionally when the system sort of breaks down and we can't do code reviewing, which happened a couple of times in the early days, there were just tons of complaints that they wanted their code reviews. We assign multiple reviewers to each chunk of code. And in fact, each chunk of code typically has 2 reviewers from the student and alum pool and 1 reviewer from the staff. And that staff reviewer's job is basically to moderate, basically to go in and review the reviews and make sure people aren't saying things that are wrong or boneheaded or rude, for that matter. We see, but we see that interaction is actually useful for maintaining the quality control of a system like this, and that's important because much of our crowd are people that are still learning, right? People that are still learning how to program and how to do software engineering. So we see examples of students correcting each other, of students clarifying what other students have said. And something I like to see is evidence that the reviewers themselves, particularly the student reviewers, are learning something from the experience. So it's not just we are getting grading work out of the students, but the students who are doing the grading work are actually getting some value from the experience. They're learning things about Java, or they're learning things about software engineering design by reading other students' code. Okay, so that's 4 examples of systems. Oh, Butler.
Has anyone tried anything like this in a MOOC?
There are definitely peer feedback and peer grading experiments happening in MOOCs. So Scott Clemmer's HCI course from Stanford uses peer grading pretty much exclusively for all of its assignments. Eric Rabkin's science fiction course at University of Michigan also uses peer grading. They use multiple peers as well, so you get graded by a handful of your other peers. One way that this system is different is that it's trying to draw on not just people who are currently in the class, but also people that have left the class and have graduated. And I think that's going to be, as MOOCs mature, we're going to have to figure out ways that we can draw on those populations in order to sort of keep the crank turning. Because
those alum were people who graduated from MIT, or just people the next year after taking the course?
For us,
yeah,
both, both kinds, right. I mean, traditionally, we have drawn on the upperclassmen already, right? I mean, the standard model of education, right, is that you're a student in the class, then you're like a lab assistant or a grader for the class, and then maybe if you become a grad student, you're TA for the class, and then, years later, you're a faculty member, whatever. It's a sort of climbing pyramid, right? And I think we'll see the same thing with MOOCs, but in a more, obviously, distributed way.
Again, you could play would be that students could pay to get more reviews.
Yes, that would be an interesting business model.
Business model.
Yes. And they may be very motivated by that, yes.
Do you know how important it is to have the staff workers actually in the crowd that looks at the submissions?
Yeah, that's a good question. And it's one that we could probably answer by looking more closely at the data, because there certainly are examples of chunks where no staff member was assigned to it for various reasons, just because we didn't have enough staff in the system that week. And so to see whether, for example, there are misconceptions that are never corrected in those.
Yeah, because like on Coursera, on the MOOC, the exclusivity students evaluate the submissions. So are there any major problems which the students will not pick on? Or
It's a good question. And I don't know enough about what has happened in those MOOCs to be able to answer that. There is definitely a fear, even in widespread QA forums like Stack Overflow, that crowd question answering can sort of propagate misconceptions around without unless there is sort of adult supervision that is keeping that from happening. But that's just a hypothesis. So I don't know. I don't have any hard answers for you, but it's a question we should all look at. Okay, one of the reasons I wanted to show you those four systems as examples was to sort of talk about what I think the future of this space looks like and why I think crowds are going to be an important part of how we think about designing systems in the same way that machine learning has become a part of how we design systems, graphical user interfaces have become a part of design systems, databases and client servers have. I think we're going to be thinking about crowds as a component, as something in our toolbox that as software designers, system designers, really, we should be able to pick up. And here's one reason why. Because crowds enable us to think about taking the Wizard of Oz prototyping technique, it's been long used in HCI and in AI, and pushing it out into the real world. So you're not just having your wizards in the lab. Your wizards are now hired from a crowd, and they're allowing you to push that app out, collect some data from real use, find out how people are using it, iterate on the idea, on the application, and then build in some AI later for performance and cost improvement. And VizWiz and Soylent are both good candidates for this. I should mention what this space is, by the way. This is the end user, that single person that wants this thing done. This is the automation, the computation, the software that is helping them do it. The history of computer science really has kind of looked at the trade-off between these two dimensions, more and more taking things that used to be done manually in paper processes, for example, and trying to automate them, trying to push ourselves down along that axis. So we have a new axis now, which is groups of people hired on demand and contributing small bits, not necessarily hired, but obtained on demand and contributing small bits of their work. So VizWiz in this space, has very little AI, it's very little intelligence, not a lot of software there. It's all pretty much being done by the crowd. But as we collect more and more pictures from blind people, right? This is a corpus that is not well represented on Flickr. The kinds of pictures that blind people take and the kinds of questions that blind people need to ask is something you really need to deploy an app out in the world in order to discover, in order to be able to train a good AI system to do it. Looking at the sort of the user peak of this, I think the end user is still going to be a crucial part of this system. There have been experiments that kind of try to look at systems that are purely small contributions from random people on the internet, mediated by some software that's coordinating them. I'm not too optimistic that a crowd is ever going to write the greatest American novel. I think you're always going to need some kind of unifying mind, some kind of designer to bring it together. And at least for practical things, this person provides the
software will read it.
Right. So it won't really matter how good it is, as long as it's grammatically correct. So that person, I think, provides the coherence. And they also have the final responsibility for the results. So we have to give them a user interface that allows them to understand what the crowd is doing and be a check on it and a guide to it. And I think we've seen there have been a number of systems that show that the user's monitoring of what the crowd is doing is very important. Soylent is sort of just one of them. There are many different crowds. Again, I don't want you to walk out of this thinking that a crowd is just Mechanical Turk, because there are lots of them. VizWiz, actually, in particular, has also been put on top of Facebook. There's some interesting results there. Actually, blind people want to have the control over which crowd their question goes to. And they actually feel more comfortable sending certain questions, actually very private and sensitive questions. They feel better about a random person the Mechanical Turk answering than about having that question end up on their own Facebook with their name attached to it. So different crowds are going to have different purposes and different uses and matter differently to the user. Our student and alumni code reviewing crowd is an example of one that we've sort of built up in the context of a single organization. So crowds can also be brought together that way and motivated by a variety of different incentives. Their grade, their reputation, maybe their desire to recruit or to hire students. A few things that we've learned about how to design crowd systems. Definitely helps to divide work into small chunks, like we did with the Soylent paper editing. It gives you more parallelism. It allows you more opportunities to do quality control. And that you should plan for noise, that your crowd is not really going to flip all the coins that you tell it to flip. They won't pay attention to all the instructions. So you have to think about quality control and think about building it into your algorithm, or try to refine your crowd. Try to get rid of the people who are not flipping their coins. That's what many people try to do. I would rather pay more attention to this because I think in the long run it will give you a more robust system. Got to think on this angle that this user is a human and this crowd also consists of humans. This is a very different beast over here. What actually is the difference between those 2 points? Why are you bringing a crowd into this system? So that crowd should provide some kind of complement. Sometimes it's that they actually have a different competence, right? That the end user may lack an ability that the crowd has, like eyesight. But another might just be that they are more diverse, or they're looking at the problem in a different way. So we had this example where, since the crowd was just looking at this paragraph, and since maybe that hyphenation wasn't actually there, they do a better job, or at least a different job, and they bring some different perspective and different intelligence. Here's some projects that we are sort of continuing to do. So building on the idea of VizWiz, we're putting a crowd into the passenger seat, not the driver's seat, the passenger seat of a car. Because the driver is, a driver as an end user is situationally disabled in ways that are very similar to the way a blind person is disabled. You're supposed to keep your eye on the road, not on your phone or your tablet or your laptop. And your hands should be on the wheel, and your attention should certainly be on the road. So we are mustering a crowd up in the passenger seat to give the driver help with essentially information needs like searching the web. We're also looking at generalizing the sort of notion of Soylent to programming, so that a single programmer in their IDE can draw on a crowd of skilled programmers from across the web and get their help for small amounts of time. So we call this idea actually micro outsourcing, rather than outsourcing a huge or large module for hundreds or thousands of dollars and days of work. Instead, you're hiring somebody for 15 minutes to write a function for you. There's a bunch of open questions. How well does this scale? How can we take advantage of crowds that are out and about? And there's quite a few startups that are doing things like that. Raising the expertise that we expect from crowds. I have some assumptions about Mechanical Turk that it's going to be low expertise. There may be some ringers in it, but we want to refine those crowds so that the ringers are not ringers, but are instead, that we have a lot of Photoshop experts, so we have a lot of programmers in there. Task routing is hard. Mechanical Turk interface is awful, awful, awful. We need much better ways to actually get a task to the person who is the best one, most likely one to do it and do it well. And then the sort of big question, how do we do these transitions from having a crowd behind your system to sensibly incorporating artificial intelligence? So that's what I've got. A bunch of places funded this, but I also want to thank the 20,000 people that did work as part of what I've shown you.
How many slides did they use?
How many slides?
They cut out from it.
Oh, I did not have them shorten my talk, no. No, but they contributed to all the other systems. by the way.
I'm just fascinated by the driving example. So this is not very practical, but maybe there could be a version of it that would be. But imagine I want to get a crowd to drive my car for me.
Okay.
So there's two aspects to it. First of all, it's real time.
Yep.
And secondly, I think people would have to come and go.
Yep. There is.
Both of those things seem to be somewhat out of scope for what you've done so far.
They're out of. So I haven't done any work on this, but work has been done on this. Jeff Bigham at now at Carnegie Mellon has done exactly what you described. Not with a car on the road, but with a robot driving around on the ground in the lab, where the crowd is controlling it basically by clicking left and right and forward and back buttons to accelerate and decelerate. And Jeff and his students have come up with actually some very nice strategies for mediating, for basically collecting the directions given by the crowd and using those to decide how to turn the robot. And the best strategy that they've come up with is one where you actually are electing invisibly a particular member of the crowd you've got right now to be the driver. That person doesn't know that they're the driver. You know, it's a bit like, you know, the Douglas Adams trope about the president of the universe is some guy on a planet who doesn't realize he's making all the decisions for everybody. That's exactly the way this works. And that person is elected by how well they're agreeing with what the rest of the crowd has done in the very recent history. And so if that person who's elected, and they only serve a short term, you know, like 15 seconds or something like that, very harsh term limits. Why? Well, I mean, they can continue to be. They can be reelected. They can be reelected. I shouldn't have described it as term limits. They can be reelected arbitrarily many times. But that way, if they disappear, we can fall back now to the next person who has the next highest agreement with the rest of the crowd over the recent epoch. So that seems to work very well. Where it sort of breaks down is where our politics breaks down. You're heading for a tree, and half of the crowd wants you to go left. And the other half wants you to go right, and you hit the tree. So, but you should certainly look at that work. It's great work. The system is called Legion, actually.
Imagine a couple more practical examples. Maybe you could hook this up to an alarm system. The alarm system goes off, and there's a couple of webcams, and people come and look and try to figure out what actually happened.
Yes.
To
Yes.
the fire department right away.
Yes.
You could use it to get my Roomba out of the difficult situations.
Yes. 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 That would probably be very. Yeah, I think there are actually probably 3 startups doing the thing that you initially described, the security camera reviewing thing. Yes. Particularly after the fact, when an incident has happened and you need to figure out who was strange and connect them together through a sequence of cameras. I think there's a couple of startups working on that problem.
So the model of a crowd so far has been a collection of individuals. There's some effort to distinguish them, but is there any effort at all to make teams out of them, or to start thinking of them as sort of little cliques?
Interesting. Yeah, not in the kinds of crowds that we're thinking about right now, but that is something that is natural to start to think of doing.
Find, verify, fix. Routines. You sort of collect a few people together. Maybe they can.
Yes. I mean, we certainly have people working together, and in many of our, so like the small group in our code reviewing system that comes together to talk about one particular chunk of code is like a team that has been formed kind of on the fly. And that's the way a lot of these systems have been done. There have been some experiments with machine translation of poetry that have brought a small group of people together and had them work together and think about how they're gonna solve this problem. But there's interesting questions about making those things last longer, or bringing those groups back.
Yeah, exactly. I mean, can one person of the group sort of call the others back?
Right. One of the assumptions I make about crowds to distinguish them from other kinds of human organization is that crowds are extremely fluid, and that any particular person in the crowd has a high probability of not being in the crowd the next time you look for them. If you lower that probability, you're getting to something that's more like a firm rather than a crowd. And then I think different rules might apply.
Thank you for your time. I think my question might relate to that point, which is it seems like having a system, the retainer model requires kind of an ecosystem of other tasks.
Yes.
So in some ways, it seems like that we need to reproduce this sense of other work to be done in order to have somebody who's available.
Yes.
Does that, I mean, so in the larger scheme of this, what can you imagine that looking like?
Well, I can imagine that there would be some tasks that have real-time requirements and some tasks that don't. And that a worker would be sort of subscribed to a feed of real-time tasks that they are willing to act on quickly when they arise. And in the meantime, they're sort of filling their time with other tasks. I mean, and this is a bit like what many sort of workers in the real world do, right? They're supposed to answer the phone when it rings, and they shouldn't let it ring for minutes and minutes before they answer it. But that doesn't happen too frequently, and in the interim, they are doing paperwork.
Another angle on what Mary just asked perhaps might be, could you find a path from crowds to firms?
Like some smooth...
Yeah, ways in which people would sort of self-organize, maybe with some assistance, and turn themselves from being extremely fluid to being more committed.
Yes, maybe. It's sort of my feeling that we already have a fairly effective system for moving people up through education and getting them into firms. And whether... Oh, so you want to speed that up? Fair enough.
It'd be totally different.
It would be different. I mean, the way that I think of crowd work, and maybe I'm just not being forward-thinking enough. I think of it as something that actually fills the nooks and crannies and the inefficiencies of our firms. The fact that many people are actually underemployed and underutilized. Many of the people on Mechanical Turk are actually gainfully employed. This is what they do instead of doing Facebook and Solitaire and YouTube at their boring desktops. They make a little extra money on Mechanical Turk. That's what surveys seem to show.
Were you focusing only on the US crowd?
No. So good, very good point. Mechanical Turk actually has two different crowds in it, right? There's a majority sort of Indian crowd that you get when you post your tasks at night in American time. And then there's a North American crowd. We did not filter our crowds. So we tend to just post our tasks without any filters at all. And that gives us basically this very bad behavior of 30% bad work. A rule of thumb is that if you take only US workers and you require them to have at least a 95% approval rate for other tasks, you're going to get a more refined and high-quality crowd. We did not use that. We tend to leave those things off because we want sort of the bad work, and we want to be able to figure out how to filter it out. Mary?
I have a question about, I just want to hear your response to thinking about what you feel human computation gives you that ML doesn't. Do you see it as complementary? Do you see it as a replacement? And I don't want to put you on the spot, but I'm kind of quizzing my favorite computer scientist.
Interesting.
And asking this question.
So, right now, human computation can definitely do things that artificial intelligence is not ready to do, that machine learning is not ready to do. Computer vision is just full of problems that it's just very bad at, and human beings are much better at. So in a sense, your question is asking me whether it will ever catch up. And I think the answer is no. I think that human beings will always be inventing new crazy ways, at least to interact with each other. Just an understanding of human culture and of human humor is likely to always be ahead of what a machine learning system is likely to be able to do. That's my gut knee-jerk reaction to that. At the very least, you're going to need the crowd to give you the training examples that you're going to have to train the system on for a little while. So, the actual, gap between the machine learning and the crowd may narrow so that it's razor thin. But I think we'll always be there.
Well, you know what Minsky said many years ago? Yes, robots will inherit the earth, but they will be our children.
They will take care of us in our own way.
Exactly.
Okay, thanks.
Okay, thank you very much.